Good afternoon. We will first finish this a few Jupyter node examples. Then after that, we will move to another very fancy part we call sampling and estimation. I think we stop at this example. Right. So as I mentioned, a neat way, or at least my way to look at this list comprehension, you try to think. There's a for loop. You write a for loop. Then you put the first statement there will be a if condition to check. Then you start to think there's some kind of list, try to append whatever you put in the output expression. So I hope this will help some of you to remove those mysterious feeling about this list comprehension. Yeah. It's just a way to design to make your life easier. Same thing, we have a for loop, and it happened we do not have a if condition here. So you do not check anything, you just put whatever element in your list, append a squared version of that. All right. So then at the end of the day, you will get another list with each of the element of the is a squared version of the corresponding element in your original list. Then for this one, we start to see there's a couple of some kind of nested flavor there. So we have data, right? So initially, let's look at what inside bracket. What you do here is you have input data. Then you try to create a new list with each element is 2 times of the corresponding element, right? But then you are not happy with that. You are doing another nested version, right? So whatever you create, the new list will start to passing into your another new for loop. And then what the actual output will be the squared version. So you multiply, then you square. All right. So we will see more nested version here. Here is a same way to think about that. You have for loop in your data, then the first condition you want to check if it is a even number. If it is, then you try to append a squared version of the other element. If this is an odd number, so basically if this condition is false, then you basically skip that element. All right. This is an example is try to show you can make those functions here be standard function, because in the slides we have C lambda function, we have C some, but there's nothing wrong if you want to make your condition check to be more fancy. For example, you want to write a code to define a Boolean function to say keep even. But inside, of course, we just put a Boolean check even if it is a even or not. But you can make it more fancy. You can say this is a lot of condition. At the end, it returns a true or false. Then you can put that function here. And for the output expression, you can, of course, create even more fancier representation as you like, right? I hope you get the feeling. We give toy examples, but I hope this give you an idea. You can put more complicated things there. All right. So this is what we have. See, you can put some interesting Boolean condition check there. So basically, you do a for loop. Inside, you check if that condition is satisfied or not. Then this is the output. The output you can, based on your function, decide what you want to output there. Just like what we put here, right? So you can have a more complicated. But if you decide to use a default if else, that's fine. That is a very simple, because a lot of time you just want to make a choice between two. So if that is the case, you can just use if else for your output function. And then the last two example, I hope you is a little bit not that straightforward. I hope you do a, so let me pay a little bit extra attention. Let's see what happens here. First, read. Take 5 seconds to read about these few lines. What is there? So in this case, if we plug in, this is a case actually it's not that sophisticated. It still follow our formula. Okay, what's more interesting is the next case, but for this case, it's not breakout formula. So you have output expression, you have for loop, you have a if condition. Okay, that is our formula. Right? Remember the formula we put in on the slides. So here let's try to decide it based on the formula. We have the for loop. This is our output expression, but it's a little bit complicated output expression. Okay, but still it's our output. So basically, you start with you create a interval object which is range 3. So you have 0, 1, 2, and then you do a for loop. So you let the I to take each of the element. So the first time I take 0, second take 1. So for each of the I, you will start to generate some output. But now this time, this output is another list comprehension. So it's nested, right? But don't worry, since it follow our formula, so it have to be work in our according to the way we understand. So basically, if I take 0, I start to be ready to generate output. But now I take a look. Hey, this is another list comprehension. Let's see what happens. So this is try to say for B in range 5. So B will take each number of 0, 1, 2, 3, 4. So let's say B take the first one, 0. So it will need to output B plus 1 and I plus 1. So B equal to 0 here, I equal to 0 here. So basically I will get 1. So I will output 1. So because this is my output expression, of course I will finish this. This is my inner loop, some kind of inner loop, the one which I highlighted. So then I will go to CB equal to the next element equal to 1. So I will say 1 plus 1, I will get 2. Then this is I still holding the previous value. Its current value will be 0, right? So I will get 2 and so on. So you will get, after you finish your current iteration, you will get 1, 2, 3, 4, 5 output. Because you can see this is you will output a list. After you do that, that means I finish my current output action. I will move to my second, the next I value, which is 1. Then I go back to be ready to produce another output, which happen to be another list comprehension. So then I will output 2, 4, 6, 8, 10. Then my I have one more left. So I go back to output another list and so on. So this is a kind of list nested, right? Use the I for loop is the outer iteration. Then this this B1, the variable B1 holding the inner one. Does everybody follow this? Okay. So remember, this is an easy one. This is just try to understand this. The way to understand this is just try to think. Now my output expression is another list comprehension. So I need to do a little bit of iteration when I need to produce anything. So which is reason I will produce a sub list within a list. Okay. And also pay attention, here you have a bracket here. So which essentially you are still having this list substructure within your list. So now my question is, if I have a matrix, I want to remove those sublists. I want to flatten it. I want to make this become 1, 2, 3, 4, 5, 6. How to do that? So the last one is the one which I just added, because I think that this is a case which is missing in the example. So here is again another way to do list comprehension, but slightly different. So the way to understand this is just try to follow the regular nested for loop. Think this is the outer loop. Then this is the inner loop. Then this is your output expression. If you read the code, this piece of code in that way, it will become very trivial to you. Think, you start to do the out loop, which is a for S in matrix, which is a S, of course, will take the first sub list, right? So the first time S we're holding the value 1, 2, right? And then the inner loop is for I in S. That means I will iterate over each element in 1, 2 in my first, basically the first substructure in my matrix. Then of course I will get 1, 2, but I remove the sub list, right? Because you just the I output is just the inner loop output. Then you will go to the outer loop to say what is the next element for S will be 3, 4, 5. But this is still is a sublist 3, 4, 5. So now I go to my inner loop to say I want to take each element in my S, the S currently holding the value 3, 4, 5. Then I will output each of the element 3, 4, 5 here to flatten, so that at end I will get 1, 2, 3, 4, 5. So this sub list structure is gone. All right. You see, we have a two nested loop there. So compare with these two examples. This example is, say, I'm doing out loop here, and it happened to within my output expression, I have a list comprehension there. But in this example, this is my output, sorry, outer loop. This is my inner loop. This is my, if you like, you can add in more for loop. You can give a try. You can probably have triple nested. So I don't want to confuse you, but I just want to show you there's a couple of different ways to use this comprehension. Yes, questions?
Make those letters I and S. Make that
Yeah, the IS is arbitrary. You can make it any number. Yeah. It's not a there's no comprehension. It's actually the IS is a bad name scheme. Yes, I just try to write this toy example for you, but in typical you probably will call this some more meaningful numbers. Any questions about these last two examples? If I hope you don't get confused by this. I mean, they are not complicated. You first of all you stick to the formula for If then there's a output expression. Stick to that, you will get most of the case solved. Except the last one. The last one is a little bit different from the formula because you're writing a for loop, then this is outer loop, then this is your inner loop, then this is your output. So this is a little bit deviate from what we present in the slides, I would say, because I include here because I know this is a pretty popular or powerful way to use a list comprehension. So I want to show you. Yeah, so your question.
So what happens if you kind of like put the inner loop first and then the outer loop?
Yeah, you will get a semantic error because when you execute the out loop, the S haven't been defined. Right? If you swap them, the S is there's no meaning for S. Yeah. So only in this way, the S is the index variable for the out loop. Yeah. Sorry.
Okay.
Great. So I will move to the lecture. So any questions for this? So otherwise I'll move to the data science part. So the topic of this class is estimation and sampling. Very important topic. So first of all, why we care about sample? Why do sampling? I think that we have covered this topic in the past few classes. So if you remember the example I tried to say, let's say I want to understand the height distribution of the Indiana people. But usually you can't measure each single one, right? Because in that case, my target is to understand the Indiana people, every single individual in Indiana, I need to measure them. So that form my population. So I call that population. So population, that means the big target, the complete target I want to start. Okay, I want to understand some parameters, okay, of that is population. Since I could not measure every single of them, in order to at least have some educated guess about the actual number or actual measure I want to understand, so I usually pick a subgroup. For example, I measure every single of you inside this classroom. You are forming a subgroup. So that is I call a sample. Okay, so the reason I could not is it's very expensive, or sometimes it's impossible to do this kind of exhaustive or measure. So I have to make a subgroup. So that is a sample. So then the next question comes, how to pick the right group, right? How to sample. So yeah, this is a definition. We often try to learn fact about population by only study a subset of population. That is a sample. Okay. Remember the definition. Okay. Sometimes it's a little bit confusing because later we will see what is a parameter, what is a statistics. We will differentiate it. So what is a fact about population? What is a fact about a sample? So this is something we make a huge difference. Okay, so this is something we will focus. So first remember the definition of sample. It's a subgroup. It's not everything. This group can be small. They can contain a very small amount of observations. It can be very large. So those make a very huge difference. So remember what is sample. Remember the definition here. Okay. So then how to sample? There's many ways. Of course, it's very important. Depends on what sample you pick, right? You will make a complete different judgment about the fact you want to know. So really, it's important. So in this class, we will focus on the first one. It's called simple random sample. This is very simple scheme. Just think in a very layman way. You just say I randomly pick a couple of observations from my population. Okay, so but the things behind that is you try to assume observations will appear with an equal likelihood. So that means you randomly pick things, they are forming a good set. So of course, the drawback is that equal likelihood assumption usually is not necessarily always true. For example, certain things is rare to observe, certain things is more often to observe, right? For example, for a certain particular very special characteristic about, let's say, a particular people, maybe you I draw 10 samples. This group of people does not contain anything about that information. So that does that assume that thing does not exist at all? It's not true, right? Because it's only because that thing is so rare and it doesn't appear in your sample. So this is a drawback of the random sample. So sometimes rare situation do not have sufficient representative in your sample. So, but otherwise, it's a very convenient, a very easy way. All right. And then another popular way is called stratified sampling. So this is try to say, can I find some attribute naturally partition my population? For example, city, a geography partition. Let's say I only take observations from a particular city. I use that as a representative to represent my understanding about the whole population. All right. So this is a try to say. Then the next stage is you first make this partition, and then you will do random sample within each of the partition. All right. So, but the drawback of this approach is what? The drawback of this approach is a lot of time it's hard to find these mutual exclusive partitions. For example, when I say city, this is a some of these good choice, right? But if think about some other mutual exclusive boundaries. For example, I say I want to study about some property about students. I will say I will partition you based on the class you take. But then this is, of course, is a bad choice, right? Because each of you may take multiple classes. I have no natural way to use that attribute to partition you, right? Do you get the feeling? Because in order to do stratified sample, you need to find an attribute which will mutually exclusive create those groups, like a city. So you are living in this city. At the same time, you can't physically live in another city, right? So you create this group. But it's often very difficult to find this parameter or this attribute. So the other one is called cluster sample. Cluster sample is slightly different from the main difference from the stratified sample. Stratified sample is to first partition your population into several groups, then you do random sampling within the group. But the cluster sampling is to say, I will try to find some way to partition your population into a several cluster. Then I will just pick that cluster as my samples. Okay. So basically, these are a couple of different methodology. Each of them have an advantage and disadvantage. But in this class, I think it's important to be aware of this, the first one, the simple random sample. So this is what we will focus in the class. So now we will have this statistics versus parameter. Okay. We differentiate attributes of the population as a sample. As I mentioned, population, we want to understand the population, but often we could not. We only can make measures or make a statement about some sample, and based on that, we want to make a good guess about the population. That is why we worry about the statistics. Okay. So first, the definition of parameter. What is parameter? The numbers which summarize a population called parameter. So those are those fact numbers, which usually we do not know. They are called parameters. For example, population mean, right? Population variance, population median. So those are the parameters. So in general, in a very loose way, population mean is the we call the average value, right? So how to calculate the average value? In a more rigorous mathematical way, to say I need to see if I make a lot of observations, right? I need to first try to see what's the likelihood each observation to make. Then I will multiply that observation value with the likelihood. Then I sum everything together. So that will give you a kind of average expected sense of a particular value. So that is what we call population mean. Then the variance is very similar. Variance is the expected value of the. I think that we have seen this how to calculate the variance. Variance is like you take each observation value, then see the difference between that to your mean, to your mean, right? Then you take a square. So you take a square of that value. The expected version of that will be your variance. So this is usually to see how spread are your observations away from your mean. Yeah. So this is another measure. The median is usually is what in the middle. Okay. Right. You see what is it? Because the mean and the median sometimes indicates a slight different things. So which is reason we usually talking about what is your average income, what is your median income, right? The median income is to see that in the middle, if you have, let's say, 100 people, maybe the people around 50, what is your income? So that is a median. Okay. All right. And those numbers which summarize a sample we call statistics. So basically, I take a subgroup, like I take this class. I can start to measure your attributes, some values. Those numbers are called statistics. Okay, so sample mean, sample variance, sample median, and this is a very easy, much easier to measure compared with the population mean. Because, for example, sample mean is simply I adding, let's say I want to see what is the mean height of this class. What I can do is I take each single measure of you. I get your height. Then I just add them all and divide by the number, total number. Then I get average mean. So for the sample mean is much easier to compute. But for the population mean and population variance, you need to think in the we think in an expected way. So we need to take count into the distribution. Yeah. So the variance, sample variance is again, I think that we have seen the code to calculate this. If you remember, in the last class, right? We first we are using a list comprehension. I remember we are taking. Or maybe, oh no, sorry. We are using the reduce function, map and reduce function to calculate this. Try to go back to recall this example. Yeah. So we have a code to calculate the variance. Yeah. So why the statistics does not guarantee to be close to parameters? They can have a huge difference. For example, I just give you one very simple example. If I just measure two people, let's say, I want to estimate I want to understand the height distribution about Indiana people, but my sample only contains, let's say, 2 people. Of course, it can be the gap can be huge, right? So then we need to really understand the problem of estimation. How to do right estimation to make better educated guess for parameter given sample data, right? So basically, the key question here is how close is our estimate to the true parameter? So this is the things we are going to study. All right. Any questions about the definition here? Are we okay with population sample parameter versus statistics? Okay. Yeah, for this class, I think that we do not really ask you to know how to calculate population mean and population variance, but we do ask you to calculate the sample mean and sample variance. These are very simple. So, all right, let me proceed. So first, if I have think about if we have a population of 1,000 people, of course, this is a for example, so we assume our population only contains 1,000 people. Okay. In reality, usually our population usually is contains a very large number of let's say individual. Yeah. So let's assume we only care about this. This 1,000 people is everything we care. So that form our population. So this will be our population some attributes. All right, this is some kind of ground truth. It's things we probably don't know, but we want to make a guess. So now let's say if we take 50 samples. Okay, I take a subgroup of this population, and I want to plot our histogram. You will say, hey, this looks like a kind of similar. Yeah, but there, of course, is not exact. So I change another 50. You see, we get something again. Another thing is not quite similar, it's the same thing, but similar. Okay, so this is the reason why we can do estimation, because every time you using sample, you get something a kind of approximate the reality, but not quite. So then we want to have some good way to minimize those estimation errors. Yeah. I do again, you see the same thing, which is close, but not exactly the same thing. We can do this forever. Yeah. So now we can always repeat. So repeat to do this sampling action. So we basically we take one sample. One sample means I take one subgroup, then I take another subgroup, I take another subgroup, another subgroup. Okay, so for each of subgroup, we can calculate the sample mean. Sample mean, as I mentioned, you just add all the numbers, all the observation together, divide by the total sample size. You will get your average. Yeah, you will get your sample average. So first time the sample average is 69. The second you get this. So each time you get a slightly different sample. So let's assume we know this ground truth. This is my population. My population mean is 69 point something, right? So this is my sample mean. So there's something close, and we want to say, hey, how good is your sample mean? Then we want to see what's the difference. We are using something we call mean square error. We have seen this. Just recall where we have seen something about this. I think that this appeared before, or at least a different version. We call integrated means integrated square error, right? But very similar concept. So what essentially you try to do is you take each of your sample mean and try to calculate the difference between your population mean. Since we do not care about the sign, we only care about the magnitude. So I take a square. Then I adding everything because xi is the I sample mean, right? You take a lot of subgroup, right? So xi is your I subgroup average. Okay. The mu here is your population average. It's a ground truth. It's like you take the Indiana people. Yes, question. Sorry. Mean square error. Mean is average. This S represents this squared. E is an error. Error is a difference. Yeah. So then the I is the like I's subgroup, right? I sample. So you are adding or over all samples, and then you divide by the how many samples you have how many those subgroups you have performed. So this will be the to test how good is your guess. Okay. So now the mean square error estimates is a 0.118. By the way, any questions about this mean square error? We will see this. We will repeatedly see this. This is one of the simplest way, or one most popular way to measure certain, like to say how good is your estimation, how good is your result. Yes, questions. N is a number of sample, right? In this case, N equal to 5 in this case, right? Because I have 5 groups. All right. So if let's say if now I reduce the number of observations within each sample. Remember, before I take 50 observations, right? Each time I take a subgroup of 50 observations. But now if I reduce, I say my subgroup, I take only 10 observations. I want to understand my population from that 10 individual. So the first time I will get this. Remember, each of the number corresponding to a subgroup of 10 randomly selected observations. That is very important. Do you get this message? So each of this number corresponding to the average of 10 observations I randomly picked from my 1,000 population. So each number represents something, represent statistics of a sample, right? The average. All right. So each of the number is not an observation, is a kind of summary of a subgroup of observation. Do we get that message? This is very important. Okay. Yeah. So try to thinking that way. Yeah. So each of the number, because each of the number is a summary of this histogram or in some way. Okay. So now we change our group size, sample size into 10. As you can see, if we calculate our mean square error, we will get 1.7, which indicates it's not as good as before, right? Before it's 0.1, I remember. So that means if we reduce the sample size or your group size, this is very natural, right? If I take my sample to be this group of people, right? I get a measure. Then if I say I'm very lazy, each time I only do a sample of 3 people, then I take that average. Of course, that average is much different or deviate from the population average. Right? I hope everybody, yes.
What does the number that the mean squared error provides represent?
What? This one?
Like the 1.7, does that number itself have any value? Or is it just like,
Yes.
oh,
You see that. I think that after the probably later slides, you will become more clear. But I can give you a very simple answer. For example, I want to see what is the population average. So one way to do that is I try to take a sample. Then for each sample, I compute the average. Then maybe I can take the average of those average. I will expect that one probably is approaching my population, right? But this essentially try to say even you do that, you are still, what is the difference you will get. Yeah. So this is try to measure how bad or how good is your individual sample average away from my population.
Yeah, but like there's a number like 1.7 itself represents.
You can compare, at least you can see the previous slides. You have this, and then you have a large number. That means your second setting is not as good as the first one.
So it's good for a comparison, like the value itself.
Yes, absolutely, absolutely. It's a lot of time those measures will just give you a criteria to decide which option you want to go. Yeah. So this is how I think that the sample mean is as I mentioned, is very easy, right? You just sum everything and divide by your sample size, and the sample variance, okay, is calculated in this way. I think that we have seen the Python code to write this by using the map and reduce, if you remember. So we will calculate the sample mean. Sample mean is just pure the average, like the average in your understanding. Then for each observation, we will see what is the difference between that to the sample mean. And then you take a square root, then you sum them all, sum each individual observation all, then divide by this guy. This is a 1 over n minus 1. N is your observation, total observations in your sample, in your subgroup. But why there's a n minus 1? So this is a part I think that usually people will get confused. So just thinking this way, this is what is going to be measured by this variance. The variance want to measure the spread, right? Basically, how samples are different from the average, right? So if you have one samples, if you only have one observations in your group, in your subgroup, what is the variance? Because if you only have one sample, your average will be yourself, right? Then you take the difference, you will get 0. So that means if I only have one sample, there's no point to evaluate the variance. You'll always have 0 as your variance because you have no variance. You only have one sample. There's no disparate things to observe. Only when you start to have 2 samples, I can have a average, right? So I can start to see how each guy far away from this average. Then start make sense. So that means at least you need to take away 1 for your degree of freedom. So if you have 3 samples, maybe your degree of freedom is 2 in terms of measure this spread. So this is a more less rigorous way to understand why you need to do 1 over n minus 1. But if you later, after you learn a little bit more about probability, you will see only you write this way, this will give a unbiased estimation to your population values. Yeah, so this is a very easily you can prove using mathematics. Yeah, but for now let's understand. Of course, if your n is very large, let's say n equal to 10,000, -1 or not -1 doesn't change much of my value, right? But this is important. Conceptually, it's important to know when you do the sample variance, you need to divide by 1 over n. In reality, if the n is very large, you probably don't care. Yeah. So are we fine with this part? Okay. And another thing is this is a standard deviation. Sample variance is a squared. So you do this, you get sample variance. Then you take a root, positive root of the sample variance. You will get a sample standard deviation. All right. All right. Just remember those terminologies: mean, sample variance, and sample the standard deviation. Yeah. So usually we denote the sample variance using using S. Yes.
Is X bar that, or the, is that X bar individual sample units, or is
Yeah,
it-
the X bar equal to first you do a summation over all samples, then you divide by 1 over A. Yeah, so you do the this is a sample mean. Yeah. Remember, usually we use a S square to denote the sample variance, and the S denote the sample deviation. Okay. And yeah, I think that we usually using the X bar to denote the sample mean, and we usually use the mu to denote the population mean. We usually use this sigma square to denote the population variance. And we usually use the sigma to denote the population standard deviation. Okay, those are terminologies. If you often you see those numbers, we never change the notation. So across different textbook, you will see exactly the same thing. So basically, I just tried to write here. You have for the population, you will have mu, you have sigma square. This is a standard deviation, variance, this mean. This is for population. For the sample, you will have, let's say, write X bar, you write S square, sorry. You should write S and S square. Yeah, so those are the terminologies. Yeah. All right. Are we fine? Yeah, so I think that I still have a few minutes. So let me talk about one of the, mostly we will review this part about the law of large number. Okay. This is one of the, probably one of the most important, how to say, the law, or this is one of the very important basics for many data science things. Yeah. So first of all, let's understand one concept. What is called IID? All right. IID is represent independent and identity distributed. So first of all, independent, that means it's very easy to understand, right? So if I have think about at the beginning of this this semester, we are doing this coffee shop examples. So if we assume people come at each day, the customer number, they do not depend on the previous day. Let's say, if we assume that. If we assume at each day, the number of people visit you do not depend on each other. So then that is something we call independent. And the second, what is the identical distributed? That means I assume the number of visit or the number of customers come to a shop, they all come from the same underlying distribution. So although each day you have a different number of customers, but they all come from the same distribution. So that is altogether it will call independent identity distributed random variable. So it's called II. All right. So this is a very important assumption behind many things. Yeah. So I will stop here, and I see you on Friday. I'll see you next week.